Our world is surrounded by numbers and patterns. Ever imagine a world without numbers? Unthinkable, right? Numbers are our primary means to quantify this universe. They are used in transactions, to measure growth, distance, dimensions. They are used in communications. They are even used to enforce control over others. Numbers define how healthy you are, how unhealthy you are. Even your worth might be determined by a set of numbers. Some days it feels like we humans are nothing but a series of numbers in a larger simulation. Despite the profound impact numbers and their arithmetic have in our everyday lives, there are certain gaps in our understanding of numbers and how they work. Through the series of videos, I am trying to address some of these gaps. But where do we start? I think we have to start at the foundation.
Axioms are rules that define different areas of mathematics. Field axioms are fundamental rules that we are most familiar with and apply to fields like real numbers, rational numbers, complex numbers, and more. Without being too technical, we will describe some of the rules. For our videos, let's take only a set of real numbers R. Real numbers generally include numbers like 34, 5, 1, fractions like 1 over 2, 5 over 6, or negative numbers like negative 2, negative 4 over 3, and even numbers like root 2, pi, exponential, and so on. For real numbers A, B, C, element of R, axioms for addition and multiplication are as follows. We have the commutative property for addition, that is A plus B equal to B plus A. Same for multiplication, A times B equal to B times A. We also have the associative property for addition, which says A plus B plus C is same as A plus B plus C. The same applies for multiplication. A times B times C equal to A times B times C. Additive identity states that there is a real number 0 such that A plus 0 equal to A for all A. Similarly, we have the multiplicative identity that says there is a real number 1 which is different from 0 such that A times 1 equal to A for all A, which seems quite intuitive. Additive inverse states for any real number A, there is another real number negative A such that A plus negative A equal to 0. Similarly, we have the multiplicative inverse that says for any real number A, as long as A is not equal to 0, there is a multiplicative inverse 1 over A such that A times 1 over A equal to 1. Finally, we have the distributive property, which is a combination of addition and multiplication. A times B plus C equal to A times B plus A times C. But the opposite is not true. A times B plus C is not the same as A plus C times B plus C, generally speaking. These axioms are the foundations for almost all mathematical computations, including our everyday transactions in stock market, communications, and whatnot. Let's accept it. We take them for granted. We can derive few conclusions using the axioms. In case of additive identity, A plus 0 equal to A. If we consider a special case where A equal to 0, then the equation becomes 0 plus 0 equal to 0. Again, using the combination of additive identity and distributive property, it is possible to prove A times 0 equal to 0. From the additive identity, B plus 0 equal to B. We multiply A on both sides. A times B plus 0 equal to A times B. Then using the distributive property, the equation becomes A times B plus A times 0 equal to a times b. Then subtract a times b on both sides will give you a times 0 equal to 0. We already proved 0 plus 0 equal to 0. Now this means 2 times 0 equal to 0. Now we already know a times 0 equal to 0, which means 0 equal to 0. Fair and square, right? But is it true? Watch the rest of the video. It might blow your mind. Note down these equations as we are going to verify them through some experiments later. But before that, I would like to discuss some discrepancies that we come across in our mathematical calculations. Let's start from a simple question that has intrigued me for years now. Assume there is a number a, where a can be any real number. A times 0 equal to 0. That is a completely valid equation as per our knowledge so far. Now if I move a to the other side, by dividing by a on both sides, 0 equal to 0 over a is still a valid equation as per our knowledge so far. But what happens if we move 0 to the other side instead of a? A equal to 0 over 0. Suddenly this has become a forbidden equation and should be avoided at all costs as per the mathematicians. I won't disagree with them. I mean, look at the equation and think about it logically. Nothing divided by nothing is something. It doesn't make any sense at all. But what frustrates me is we don't have a valid reason as to why this keeps happening. Also, a equal to a is true for any number including 0. It also means a over a equal to 1, which we already know from the multiplicative inverse property. And it is true for any number except 0. Why? Why is there an exception for 0? Why can't 0 over 0 equal to 1? Finally, this is my favorite one. A times 0 equal to 0 and b times 0 equal to 0, where b not equal to a. We already know 0 equal to 0. So, a times 0 equal to b times 0. Dividing by 0 on both sides should give a equal to b. But for some unknown reason, division by 0 is not allowed. What is the problem with all these mathematicians? Why can't you let number 0 do his thing? Why so much restriction on number 0 when it comes to division operations? We need answers.
Through the next set of videos, you will have a better clarity on why things the way they are. And for that, we need to see things from a slightly different perspective. From now on, we are going to use experiments to make some discoveries that might help us better understand some of the flaws that we encounter in our everyday computations, especially using number 0. For this first experiment, I want you to get your earphones. Kindly decrease the volume of your device to maybe 50%, after which I am going to play a test audio and I am going to decrease the volume of this test audio until it becomes inaudible. In case test audio is still audible for you, you can decrease the volume of your device further. You can pause the video here to sort things at your end. From now on, the required instructions will be displayed as text on screen so that it becomes easy for you to follow. So this was a very simple experiment to prove a point. Audios 1 to 5 were all inaudible, right? So we could assign values 0 to each one of them. But when we added all these audios together, the final output was audible, which means a non-zero value. I mean, how did this come to be? How can 0 plus 0 plus 0 plus 0 plus 0 equal to a non-zero number? Very counterintuitive, right? Let's do a part B of the same experiment. I want you to get your earphones and I want you to keep the volume of your device to maybe 50%. But this time, I'm going to play two audios one at a time. I want you to tell me which audio is louder, audio 1 or audio 2. The only way to figure out the answer is by multiplying both audio signals by the same proportion. And that means multiplying both audio signals by a number of maybe 10, 20 or even 100. Let's play amplified audio 1 of case 1. Alright. Playing amplified audio 2 of case 1. Audio 1 was louder obviously. I couldn't figure it out. What about you? Let's play amplified audio 1 of case 2 now. Alright. Playing amplified audio 2 of case 2. Got that. Again, audio 1 was louder than audio 2. Now for the part B of the experiment, both audio signals were inaudible. Audio 1 was inaudible and audio 2 was inaudible. That means audio 1 was 0 and audio 2 also was 0. But when we heard the amplified versions of audio 1 and audio 2, we could understand that audio 1 was louder than audio 2. So from this experiment, it kind of proves that 0 plus 0 need not be equal to 0. And at the same time, 0 need not be equal to another 0. It seems wild, right? Some of you might not be convinced with the current experiment, so let's try more experiments.
The next experiment is a visual one. This experiment can be done with the help of any 2D or 3D visualization software. You can see a completely blank white screen now. But can you also spot a filter? Here, I can move it around. I can also zoom in. You are not able to make out the contours of this filter because it is transparent, or in other words, has zero opacity. So it will let all the light pass through from the white surface behind it. Arrangement looks something like this. Let's assume the white surface is a light source and emits 1000 lumens of light. The filter having an opacity of 0 will let all the light pass through. So the equation can be written like this: 1000 times 1 minus 0 equal to 1000. Opacity is a fraction of incident light that does not pass through a material. So 0 opacity means all light will pass through, and an opacity of 1 means all the light will be blocked. Now I am going to add more filters with the same opacity as the current filter. The arrangement will look something like this. Since the filters are transparent, we should still see a blank white screen. No matter how many filters I add, the output should not change. That is, 1000 times 1 minus a times 0 should still be equal to 1000, where a is a number of filters. Let's find out anyway. I have duplicated the current filter and stacked them over one another. But you can see the region got darker. 1000 times 1 minus a times 0 is less than 1000 now. It is only possible if a times 0 is not equal to 0 in this case. In case you don't trust me, I can rearrange the filters and stack them back. Here, let me try that. Again we proved a times 0 is not equal to 0 through an experiment. Now we have two filters on screen. Can you tell which of the two filters is more opaque? Left or right? The only way to figure it out is by duplicating the filter the same number of times. Here we go. Left one seems more opaque, even though they were both equally opaque to most of us watching the video. There you have it. 0 is not equal to another 0.
Let me thank the sponsor of this video, Infilling Global. In this era of deepfakes and voice clones, it is really important to equip ourselves with technologies that limit unauthorized access to our virtual accounts. Companies like Infilling Global are developing technologies to tackle this menace. They have developed VOBI, a unique voice biometric technology that can be used to authorize customers over phone calls and conference calls. Their technology is very resilient to voice clones because of their state-of-the-art liveness detection. They have three product offerings: Voice OTP, Voice Key, and Voice PID. Do check their website and connect with them to secure your organization using their technologies. Link is given in the description.
For the next experiment, we are going to use weighing scales. But before that, I would like to discuss a concept. Every instrument has a minimum value that it can measure or detect accurately. For a 150 mm ruler, it could be 1 mm. For a mechanical clock, it could be 1 second. For an accelerometer, it could be a force of 0.1 millig's, and so on. Some engineers might use the term least count for the smallest measurable value, but I would prefer to use the term resolution. Going forward, we will use the term resolution for the smallest measurable value using any sensor or instrument. Even our eyes, ears, and skin are like sensors that can measure light, sound, and touch intensities. But these sensors have different resolutions that vary based on individuals. I have two weighing scales. The one on the left claims to have a resolution of 1 gram, but the minimum I was able to measure was 2 gram, and it is a cheap one that I purchased online, so it is not very accurate, but good enough to prove our point. The one on the right has a resolution of 0.01 gram and works fine. I am going to use legume seeds or green gram as samples on a piece of paper. I have 3 samples ready and have marked them individually. I will weigh each sample on a bigger weighing scale first. Here are the readings. They gave a reading of 0 gram for each sample. Now I will weigh them together. The reading shows 2 gram. How is this possible? Let me weigh them individually using the instrument with small scale. The readings say 1.17 gram, 0.92 gram and 0.98 gram for samples 1, 2 and 3 respectively, totaling a value of 3.07 grams. It is possible that the larger scale needs a threshold of maybe 3.2 gram to detect as 3 gram, which we don't know at this point. Unfortunately, I won't be able to weigh them together on the smaller scale without mixing the samples. The bigger scale has lower resolution, so the readings for individual samples were 0, which ideally should mean all 3 samples have the same weight. Unfortunately, that is not the case. So again, 0 is not equal to 0 and 0 plus 0 plus 0 need not be equal to 0. Let's pause for a moment and think about it. For this experiment, I used instruments with resolutions of 1 gram and 0.01 gram respectively. But we can extend the idea to instruments with resolutions of 1 microgram or nanogram or 10 to the power negative 14 gram and so on. Because of the limited resolution of any instrument, it cannot accurately measure beyond a certain small value. Every instrument more or less operates like this graph. For example, say the resolution is 1 gram, then it will output a value of 0 until the weight threshold crosses 1 gram. Output will be 1 gram until the threshold crosses 2 gram. The same goes for 2 gram. Instead, if the resolution is 0.1 gram, again the instrument reading will be 0 until it crosses a threshold of 0.1 gram. It will output 0.1 gram until the threshold crosses 0.2 gram and so on. Even the threshold values might not be exact, like it could be 0.11 gram, 0.21 gram, 0.31 gram and so on.
For the final experiment, we are going to use a multimeter.
A multimeter is a device used to measure everything electronic, like voltage, current, resistance and whatnot. For now, we will use it to measure voltage across a resistor in a simple circuit. I have connected 3 resistors in series with the power source. We will check the voltage drops only across the first 2 resistors individually and then combined. For the sake of this experiment, we are going to ignore the third decimal place of the multimeter. I am getting 0 volts across the first resistor. Also getting 0 volts across the second resistor. Now let's check the combined voltage across both resistors. Ideally it should be 0, but no, it shows non-zero value. Let's check the voltage in the millivolts range for both resistors individually. Both of them show different values. So yeah, 0 is not equal to 0 and 0 plus 0 need not be 0. Let me go back to the previous plot. This plot will be similar if we are measuring other quantities like liter, milliliter, degree Celsius, degree Fahrenheit, kilogram, pound, second, millisecond, picosecond, radian, degrees, ampere, milliampere and so on. Why don't we generalize them all into a term called unit instead? Yes, let's do that. Now let me try to convince you for one last time why 0 can never be equal to another 0. Assume the resolution of our device is say 0.1 units. Then 0.01, which is less than 0.1, will be recognized as 0. Similarly, 0.001 will be 0. 0.0000001 will be 0. 0.0000001 units will still be 0. 10 to the power of negative 20 will be 0. 10 to the power of negative 100 will be 0 as per the graph. In what world can we say 0.0000001 equal to 0.01 when 0.01 is clearly 10 to the power 5 times bigger than the number on the left, or 10 to the power negative 100 equal to 0.01. I hope you understand where I am going with this. The smallest number that will be recognized as 0 is 10 to the power negative n, where n is a very large number. The largest number may be 0.09999. Just imagine the scale difference. This problem happens only for number 0. Let's take the case of 0.1 unit instead. Smallest number to be recognized as 0.1 could be 0.1000001, and the largest number to be recognized as 0.1 could be 0.19999, and the difference in the scales is roughly 2, which is not bad compared to 0. As we measure higher values, say 0.2, 0.3, 0.4 units, the scale gets smaller. You can extend the idea if the resolution is 0.01 units or lower. As the resolution of the device improves, things get better for non-zero numbers, but the problem will continue to exist at 0. Feel free to work out the math by yourself. So that's it, folks. Assuming 0 equal to 0 is completely false. In fact, 0 is that number once you measure it stops being 0. Just think about it. How can you compare something that you can never measure? I would like to end this video using probability to prove to you that 0 plus 0 need not always be 0. 0 is a spectrum of numbers less than the resolution of the measuring instrument. Now assume the resolution is say 1 unit. If we have two zeros, Z1 and Z2, where Z1, Z2 less than 1 unit, the probability of Z1 plus Z2 equal to a non-zero value will be 1 minus probability of Z1 plus Z2 less than 1. That is 1 minus P of Z1 plus Z2 less than 1. We can figure this out mathematically, or we can use simulation. I, being an engineer, prefer to use simulation. But for more accurate results, it's better to use traditional math. This is a plot of the graph, and the final probability value is approximately 0.47, which means out of 100 times you try to add two zeros randomly, 47 times you will end up getting a non-zero value. But if you try adding 3 zeros randomly, 83 out of 100 times you will end up getting a non-zero value. Finally, if you try adding 4 zeros together, 93 out of 100 times you will get a non-zero value. Probability of getting a non-zero value increases with an increase in the number of addition operations. Surprising, isn't it? I have intentionally avoided discussing the negative numbers of the number line for this video. We will cover them in the coming videos. Here is a summary of this video. We know a plus 0 equal to a from the axioms, but to me, this is not always the case. So we will put an asterisk to denote not always. 0 plus 0 equal to 0 is not always true. A times 0 equal to 0, again not always true. 0 is one number. I completely disagree. 0 is not one number, but a spectrum of numbers less than the resolution of the measuring instrument. We will explore this idea more in the coming videos. 0 equal to 0. This is another statement that I completely disagree with. 0 can never be equal to another 0 ever.
The conclusion of these experiments might surprise many. Everything boils down to one simple idea. 0 is the smallest unknown number that you can never measure. Just think about it for a moment. In the next video, we will finally address division by 0.